So the primary utility of radical reactions is to selectively functionalize a alkane. And I initially showed to you what happens if you take, say, cyclohexane, which has 12 of the same kind of hydrogens on it, and you expose it to bromine in the presence of light. What happens is that the light causes the bromine to fragment to initiate the radical reaction, and then at the conclusion of the radical reaction, you have now installed a bromine, and again, all of the hydrogens are the same, so you end up making specifically that. Now, as it turns out, there's no particular advantage to doing that with bromine or with chlorine if you are trying to functionalize material that has no real difference in any of the hydrogens. Chlorine works fine, bromine works fine, chlorine's more downhill energetically, so it may actually work better. Bromine, well, it has other advantages, we'll talk about that later. However, the other thing I should point out here is that fluorine gas will unselectively react with absolutely everything, and anything that's organic will react with fluorine gas. It's an excellent way to start a fire. Take some organic material, including you, and expose it to fluorine gas, and there's a decent chance you start a fire, and if it's reactive enough, there's a decent chance it actually explodes. So radical chemistry is something that happens with all of the halogens, at least in principle, and fluorine is a completely uncontrolled reaction, and you don't want to try it at all. Whereas I2 can participate in radical chemistry, but it's not downhill to functionalize alkanes. So we can't use I2 to react with simple boring alkane in a radical fashion to provide a new carbon iodide product. So instead, we have really two tools, bromine and chlorine, and like I said, chlorine's going to be faster, bromine's going to be more selective. Now, again, with this system, it doesn't matter. Right now, what we have is 12 hydrogens, all of which are the same, so it doesn't matter if you use bromine or chlorine. However, if you have a system like this one, where there's a clear, unambiguous difference between the kinds of hydrogens that are present, then the choice of chlorine versus bromine becomes really important. So note that we have three different primary type hydrogens, one set of secondary hydrogens, and a single tertiary hydrogen. The chlorine can react with all of those reasonably unselectively. If you react with bromine, however, you make primarily the tertiary product, and just the tertiary product. It's not entirely the case, we'll walk through the data a little bit in a second, but with bromine, you essentially make one thing, and it is specifically substituting the tertiary position for a bromine, and that will end up being synthetically useful. And in fact, when we work through the math, you'll find that you can achieve this product in something like 90% yield. So it's really possible to make that, largely that, and then have it be synthetically useful. The chlorine, however, is going to be much more indiscriminate. It's going to tend to react with everything, and so we'll end up making this list of products. Obviously, you're going to make at least some where the chlorine has substituted for the tertiary position, as before. There are two secondaries. You can substitute for either of those, and of course, you're going to make both enantiomers. If you substitute at either of these two primaries, what you actually end up doing is creating a pair of enantiomers, and it doesn't matter whether you substitute at this one or at this one. Again, you're going to end up making a pair of enantiomers there just by adding the chloride. Now all of a sudden creates three unique things bound to the central carbon. So again, you add a chloride, you create a pair of enantiomers, and that's a mess. You do, however, have a primary position that's functionally different than these two, and so if you add there instead, you end up making that. Again, you will end up making all of these products simultaneously, and that's kind of a mess. This table is really the key thing to recognize about radical selectivity, and the core idea is that you have two different potential halogens you could be using, the chlorides and bromides, but we can measure the relative rate of reaction. And if you set the rate of the primary to 1, then it turns out that reacting with a secondary and reacting with a tertiary is going to be faster and faster still than the primary. And that's entirely because a primary carbon-hydrogen bond, which is the thing that you are abstracting, is stronger than a tertiary. So a primary is on the order of 100 kcals per mole, and though the tertiary rounds to 100 kcals per mole, it's less. It's like 97, and a secondary is like 99. So anyway, having a primary, it's harder to pull that CH bond off. Tertiary, it's easier to pull that CH bond off. And so that's the source of the selectivity. I'll walk through this more in a separate video, but the key thing to understand is it is easier to remove a hydrogen from a tertiary position, and therefore you're going to get some selectivity. But this chlorine is relatively unselective. You're going to make substantial amounts of all products, whereas the bromine is much more selective. Thousands 1,000 times more selective than the chlorine is. Well, that's an exaggeration, but you get the idea. The difference is not small. We're talking about 3 orders of magnitude. So the bromine is vastly more selective. And you'll get a sense for that when I diagram out how much of each product you can expect to make. Okay, so here we have the fancier table from the Miller handout, and it's really a way of making the case of just how selective these different rates end up being. And so earlier we walked through the total number of hydrogens involved in this molecule and how many different kinds of hydrogens were present in the molecule itself, how many primaries, how many secondaries, how many tertiaries, and so on. And so basically you have 9 hydrogens that are primary, you have 2 hydrogens that are secondary, you have 1 hydrogen that's tertiary, and that applies regardless of whether we're talking about a chlorination or bromination. But the relative rate for a chlorination primary is going to be 1, and for a chlorination secondary is 4, and for a chlorination tertiary is 5. And so what you do is you then just simply multiply these to figure out how often statistically you end up getting the various outcomes. So in other words, if you take your 9 primaries and they all have a relative rate of 1, then we make 9 molecules that are substituted on the primaries. So say this guy, this guy, this guy, because there's 3 hydrogens in each of those positions, you end up making 9. And of course, they're not all the same molecule. We have different enantiomers and so on, but let's ignore that for the moment. There are 9 outcomes where you have done a substitution at the primary. Now, there are only 2 secondary hydrogens that could be swapped out. However, that happens 4 times faster, so you actually end up making 8 molecules substituting at the secondary position. And there's only a single hydrogen that's tertiary, but you react with it 5 times faster, so you end up making 5 of those molecules there. And if you just simply add those together, what you find is that together, those are 22 outcomes. And the one we care about, presumably trying to isolate a reasonable amount of stuff, is going to be the tertiary. So what we make is 5 out of 22, which is not a high percentage. On the order of 20-ish%. It's not good. Meanwhile, if you are walking through the exact same analysis for the bromide, well, again, we have 9 potential primary products, and I haven't drawn them out, but it would be the same, just bromines instead of chlorines. So 9 potential, and again, the relative rate for the primary, we define it to be 1, so we make 9 of those. It starts exactly the same. However, here's a big difference. Rather than making 4 times as many secondaries, we make 80 times as many secondaries, and there are 2 such hydrogens, so that we actually end up making 160 of the secondaries relative to the 9 primaries. And then, of course, we have 1,600 for the tertiary, which means we make 1,600 possible products with the substitution at the tertiary position as opposed to primary or the secondaries. Add these all together, and what you get is 1,769. And so your desired product is going to end up being 1,600 divided by 1,769 for your yield, and that's not bad. Now, you're going to get more than that in theory of your product, but then when it comes to actually purification and isolation, you can achieve a 90-ish% yield of this stuff. Your best case scenario isolation of the tertiary for the chloride, 20% maybe, and you're going to have a whole mess of products. Here, you're going to have a whole mess of tiny amounts of the primaries. You're going to have one major thing to try to get rid of, and there's maybe 10-ish% of that. Again, 160 divided by 1,769, that's on the order of 9% or so. And so what you're really trying to do is you're trying to get a 90% spot away from a 9% spot. That's not that bad. And there's one dark spot on your TLC plate and one lighter one. You can separate those out relatively easily by column. Whereas here, what you have is a giant streaky mess of everything, and the one thing you're going for is not even the darkest spot present. Or it might be, but it's on the same order as everything else. So anyways, this is a tough purification problem. This is a relatively trivial purification problem, not to mention the fact that you made vastly more of the stuff you're interested in from the outset. In other words, if you are interested in running a selective radical reaction at all, you have to use the bromine, cannot use the chlorine. Chlorine's just not that selective. These are basically all the same. They're not, but given the number of hydrogens of each type likely to be present, they work out to be essentially the same. Whereas this selectivity difference is massive, and you can absolutely run a reaction at the tertiary position as opposed to one of the others selectively and isolate useful amounts of stuff.